Alright, you can write this down. So this is our next topic.
Will we do it again in viscosity?
We don't really talk about viscosity. It's more going to be in this one. I mean, we talk about viscosity, but not formally in this. Okay, do you have this? Yeah. Wait. Okay, so we kind of had a question where I asked you what is the force that makes the apple accelerate when it falls, and of course you all know this is a gravitational force. So gravitational force is the force of attraction between all matter, and normally this is only felt when the object is extremely large. So in other words, when you're near an Earth, Moon or Sun, you can feel it pulling towards you. Like right now we can feel it pulling down. So you could get this definition in the exam, although it's not very likely, and it's a pretty simple definition. It's the force that attracts all matter to each other. And you don't even have to write the normal part down, so like this is it. And it's normally you can only feel it when it's very large. Although if you had very sensitive equipment, you can detect it for smaller objects.
Magnets.
Yeah, but that's a different type of attraction, yeah.
But it's still a force.
True. But not the one I'm interested in today. Okay, we got this. Gravitational force is the force of attraction between all matter. I haven't looked at that link you sent me yet. I have to have a look at it. Because I still feel unhappy with it. And I won't feel happy until I understand it. Okay, continue? Yep, alright, great. Gravitational force is what keeps you on Earth and not floating in space. So the weight of an object is defined as the gravitational force. So in other words, weight is the force due to gravity. Again, you can write that down. It's good practice for English. Oh, at least pretend to write something down so I'm not just looking at you. Come on. I know, but even pretend to write something now. It'll make me feel better. Even if you're writing down your shopping list, I want to at least pretend you're making notes, okay? Okay. So we'll have a look at a little bit of a calculation now. Got that? Yeah? No? 5 seconds. I'll tell you what, I'll give you 7 seconds because I'm so generous. You didn't even need 5 seconds. Okay. So, we know, here's my picture up. When something is falling, what's its acceleration? 9.81, which we called G. So force is equal to ma. M, we can know it, and the A we know is G. And the force, what's this force called? Weight. So in other words, weight is just mg. That's all. So this is like our first formula, very, very simple formula. Weight is mass multiplied by gravity. G is always 9.81, yeah. On Earth. Okay, got that? Weight is W, M is mass, and G is gravity's acceleration. Right, so here's a short question for you to try. It only take you 7 seconds to do. Calculate please. how much does a 2 kilogram physics book weigh on Earth? So what's the weight of a 2 kilogram physics book?
1.98.
No, not even approximately.
You're on it.
Not even close.
19.62.
19. You're a decimal point off. 19.62 newtons. Yeah. How much does 2 kilogram physics book weigh on the moon? And the acceleration due to gravity on the moon is 6 times smaller than what's on Earth. So it's g over 6 for the moon.
3.27.
Sorry, what did you get?
3.27.
3.27 newtons. A 2 kilogram physics book weighs 4 newtons on an asteroid. What is the mass of the book? Correct. I'm trying to trick you here. It's 2. Mass is always 2. It doesn't matter what's going on. Right. So, which will hit the ground first? Which one will hit the ground first? You see, you got tricked there. I tricked you. It does matter.
They both touch the ground first.
No, they do not.
Together.
They do not. They certainly do not. Yeah, exactly. Yes, Omar. Yeah. Let's do an experiment. One bowling ball, one feather. Drop it. Real life. Which will hit the ground first? Yeah, we only deal with real life in physics. Okay, this isn't biology or something. So the bowling ball will hit the ground first. Of course, you know this from your experience of dropping feathers and bowling balls. Okay, so the bowling ball will hit the ground first. But there's a tiny complication with that. So if we look at the picture for the bowling ball, here's the bowling ball, and then here's the feather. We have U, V, A, T, S, and let's just keep it simple. We'll say the S here is 1 meter, and here is 1 meter, and they both start from rest. So the U is 0, and here the U is 0. The V we don't know, the V we don't know. The A is minus 9.81, and here we think the A is also minus 9.81. The T we don't know, the T we don't know. The S is minus 1, and the S is minus 1. So, because the information here is the same, then we calculate the time as being the same. But in real life, this is not what's happening. Now, this here is because of the weight. And this one here is provided by the weight as well. This is where it's different. What we're not considering is, in real life, there's another force here. Air resistance. Whereas here, there's not really another force here. And we cannot ignore this because it is making a big difference in the time. So in real life, we have an extra force to consider. Now, you called it air resistance. That's true. There's another more general... not trust. Trust is the... Yeah, so what's the... no, the opposite of trust. Trust is going forwards. We want the one that's going backwards. Bit more general than that. No. Yeah, friction. Yeah. We call it drag. Yeah. So the trust is what drives it forward, and the drag is what is acting against it. So you definitely need this vocabulary. Okay. So if you want to draw or write it down or whatever, we have trust and we have drag. Thrust, or trust, as I say. What? Okay, do you have this? Yeah. Now, terminal velocity. So, it's the maximum velocity a fallen object can have. If we go back to this example, this is only going to get faster and faster as it falls. But with the feather, it doesn't get faster. If you picture it, it kind of moves down at the same speed. What's happening here, as it falls, this force will get bigger and bigger until this force will equal this force. And then at that point, it no longer accelerates. Its speed stays the same, and this speed is called the terminal velocity. Just to be super clear here, F equals ma. That F is total force. So in this picture, it would be W minus drag is ma. Yes, and when it reaches the terminal velocity, these two are equal. So this should equal 0, which means then that the A is 0. And if it's not accelerating, it's traveling at a constant speed. So terminal velocity is the maximum velocity a falling object can have, most commonly seen with the parachuter. So although he jumps out of the plane and he will accelerate, he does not accelerate forever. He reaches a maximum speed. Yeah. Okay, terminal velocity, I'll tell you now, they have asked for the definition of this in exams before, so maybe you want to note that beside your definition. It could be in the exam. It's the maximum possible velocity a free falling object can have. And usually we only use terminal velocity to describe falling objects. Although, I suppose it doesn't have to be falling. Okay, do you have this? Yeah. Yeah. Continue. Now, something important to note about drag. Drag is often proportional to speed. This means that as he falls faster and faster, the drag force increases. And in fact, this makes it very difficult to deal with mathematically. Too difficult for this course. So we'll have some tricks to deal with it approximately. But just so you know, in real life, the drag is not constant. It increases with the velocity, makes it hard to calculate, and so we'll have some shortcuts we can use to simplify. So we kind of ignore this in the question, or at least we kind of work around it. Again, we don't have to write this one down. This is one I want us to think about right now. A car of mass m starts at rest and accelerates by means of a force. The driver keeps his foot down but does not continue to accelerate forever. So why, in other words, why do cars have maximum speeds?
Because of the shape of the car and the air resistance.
Yeah, a bit more precise though. This is the idea, but what precisely is happening? Yeah, so what exactly is happening with the car?
The drag and the thrust are equal.
Yeah, but what is the drag? What is the thrust? Like, thrust
is like the power of the engine.
The thrust is coming from the engine, which does not change. That's constant because it depends on the engine. 2-litre engine will have a certain thrust. As the car accelerates, what happens to the drag? It increases proportionally until the drag equals the thrust of the car, and the car cannot go past this. Okay, so let me think. Car engines, their power, so to speak, is measured in horsepower. So what would be, I don't know, something like a mid-sized car, horsepower, 200 horsepower. So 200 horsepower car would probably get you to 180 kilometers an hour, something like this. Yeah, I mean,
yes,
my first car was a Toyota Yaris, and I got that at 169.
You can actually
Yes.
the air was going with you.
Yeah, no, the car, well, no, it was an empty motorway. There was no traffic in front or behind me. I could see, it was a clear day, so I could see about 2 kilometres in front and behind me. There was no one around. I said, let's see what the maximum is. We'll conduct an experiment.
But it says 200 on the...
Yeah,
That doesn't mean you'll reach 200, no. So, about 169 for about 200, no, I think a Toyota Yaris is only like 150 horsepower, 140. Yeah, it's small. I know, maybe 4-cylinder. No, it's 1 litre.
Oh, 1,
Yeah. So anyways,
there are no speed limits on the highways over here?
oh no, there are. If you want to go to like 200, 300, you have to increase the horsepower from like 140 to 1000. Like a Bugatti Veyron is 1000 horsepower, isn't it? I think so. In other words, my point is, the faster you go, the drag increases so much dramatically. Okay, so it's really difficult to overcome the drag from air resistance from cars. So like I said, it might be easy enough to get from 0 to 169 kilometers per hour, but 169 to 269 is going to be much more difficult, and then 269 to 369 even much more than this. Yeah.
If you break the sound barrier,
Yeah.
do you get rid of the drag, or
No, it's still there.
does it become any less?
No, it doesn't. The only thing you can help to reduce the drag is the shape of the car. There's not much else you can do other than the shape. Or if you're in a vacuum in space, that would be quite helpful. There's no air, yeah. Okay, so again, this is just another question to think about together. A coin is dropped from a 100-meter building. How long would it take to hit the ground? So I want you to calculate the time and then answer if it'll be more or less than this. But first calculate the time. So it's 0, 9.81, and S is 100. Calculate the time for me. Huh? Oh. Okay, what time did you get?
.5.
Yeah. 4.5 seconds. In real life, will it be more or less than 4.5? No, I think.
More.
Yes. Yes, sorry, more.
There we go. Thank you. It'll be more because the drag will reduce the acceleration to maybe 9 instead of 9.81. So it'll take longer to hit the ground because it will gain speed slower.
So
Yeah.
how did you calculate it?
Oh, you know it. UVATS.
Oh.
That's all. Nothing special. Okay, continue. Right, now, this is the first real question on this lesson. So, I'll do this one. I want you to carefully either draw or write the information down, whatever. I'll do this one. I mean, you can try it if you want. It's a bit hard though. So I'll just give you 1 minute to write this or draw this. A beaker of oil. So you have, this is a beaker of oil, and you drop a steel ball in it. So if you want to draw it or write it down, whatever. What do you need, Omar?
I didn't understand.
Which? This?
No, the last question.
Ah, the last one. Yeah.
No,
So
not the last one, the beaker. The one you just said.
oh, beaker.
Yeah, the beaker.
It's like a tall cup in the lab. You know, you pour liquids in it. You can see the different heights. Okay, you drew it. We can look at it now. Okay. So, watch carefully. This one's a little bit tricky. So we have a beaker of oil, and we put the ball inside of it, and it sinks to the bottom. It starts at rest. We know this. V we don't know. A we don't know, because it's not 9.81. I mean, how tall is this? It's 80 centimeters. If it was 9.81, 80 centimeters, the time should only be like this. So 10 seconds means it's slowly sinking. So the A is definitely not 9.81. The T we do know it's 10, and the S is minus 0.8. Because we'll say it falls down 0.8. So what can I calculate here? I can get the A, right? So what will give us the A? S equals U T plus a half A T squared. So that's minus 0.8 equals 50A. So A equals of course 41. No. Minus 0.016 meters per second squared. So you might think, so I know what the force is. Well, not quite. Because the picture is a little bit more complicated than this. Let's picture the ball right here for the moment. What force is on this ball?
Weight and drag.
Weight and drag, yes. So there's actually two forces. So in your F equals ma formula, that F is the total F. That's not this force, the thrust. It's not this force, the drag. But it's this force minus this force. Okay. So we have a slight problem here. At the very beginning, what's the thrust? It's the weight. In the middle, it's still the weight. And at the end, it's the weight as well. At the beginning, what's the drag?
0.
It's 0 because it just started. Did you get that?
Yeah.
At the end, you have the maximum drag, which we call D. But it's changing. So what are we going to do? Because if it's changing, we can't use our formulas. So what could we use instead? Roughly.
An average.
We could use an average, couldn't we? So instead we could say the drag, roughly 0 plus D over 2. So in this formula here, we could use an average drag. So we could say basically the F is the weight minus the average drag. I'll just write average drag like this. And that's equal to M. What did I say the M was? 0.1. Now actually, I'm taken down as negative, so I'll write minus W plus D over 2 equals M, which is, sorry, what was it? 0.1, and the A is minus 0.016. Because I'm taken down as negative and up as positive. Negative, positive, yeah, okay. And we actually have a formula for W. What's the formula for W? It's mg. So that's 0.1, and that really is G, 9.81, plus D over 2 equals 0.1 times minus 0.016. Now, do I ask for the drag at the end, or the average drag, or what did I ask for? The average drag. So that's the D over 2. So D over 2 equals, so let's calculate it, 0.1 times minus 0.016 plus 0.1 times 9.81. So this comes in at 0.9794 newtons. That's the average drag. Now, like I said, this is a very difficult one, maybe to get your head around. So please write it down carefully. You don't look happy.
We used to get the drag for each place.
Yes, and you'll be shocked at how close this is to the true answer. Because I calculated it, like you said, by each second, and it'd be less than 1% error.
Yes, but this is so simple.
I know. So I don't know. Are these tears of happiness or sadness? I don't understand. Which is it?
Not happiness.
Okay.
So we divide the thing by 2.
No, I didn't even have to write in D over 2. I could have just said average drag. I just want you to understand that
value divided by 2.
this one?
Yeah.
No, this is this.
Oh.
I didn't do anything with the 2. In fact, forget about this if you want. Just say this equals the average drag. I'm just trying to explain what I mean by average drag. It's like halfway between the smallest and the biggest.
Okay, and that's halfway.
And this is halfway.
Don't you have to divide it by multiply it by 2?
If you multiply it by 2, what you've worked out is the D, which is the drag at the end, which is the maximum drag. So if I said to you, what is the drag at the end, you would. Now, just be careful with the signs. I wrote the equation as minus W plus D over 2 equals minus 0.1 times 0.016. But you could have said this force minus this force equals the mass by acceleration. So you could have said W minus D over 2 equals 0.1 times 0.016. So you notice that these equations are actually the same. The only difference is you multiply by minus 1. So you can be flexible with the signs. Just whatever you do, if you decide, stick to it for the rest of the question. So in the previous example with the man jumping off the building, I just took down as positive, which is fine. Just make sure you stick to that for the question. Okay. Do we have this nearly? Have you seen stuff like this before or not? You have?
I don't remember.
You don't remember if you have or not yet?
Can we check this calculator if this is the one we're supposed to have?
Yeah, show me the picture. That's the one. I can tell from here.
Yeah, sure?
Yeah, 100% sure.
Okay. Yeah,
I know my calculators. That's the one. Yeah. Okay. Continue. Yeah. So we have some questions here. So what we can do. What to do? I want you to try this. But I wonder, should I let you try it and then should I do the answers, or should I let you try it and finish it at home?
Right. Isn't this now the math lesson?
No, it's a double class, isn't it? And then maths at 4.
Yeah.
Let me see what the next topic is. No, the next topic is a difficult one. No, okay, I'll tell you what, we'll work on this for a few minutes, and then maybe I'll give you the answers as well. So if you can try and get these done in maybe about 10 minutes, maybe? I don't know, how long does it take you to do your homework?
More than, yeah.
Are we talking on the scale of hours, is it?
No.
No. Half an hour?
20 minutes.
Okay, after 10 minutes you should have question 1 and 2 done. Question 3 and 4 is a bit tricky, so yeah, okay, that's what we'll do. Do 1 and 2, and then you can try 3 and 4. You might find it a bit hard because it's like this one. But you should be able to do 1 and 2 now. Yeah.
Are we going to start project time?
We'll see. I'll see how you feel about this.
I would like a break long enough for me to eat before my math lesson.
Oh yeah.
You didn't have any lunch?
No,
Because
we didn't have breaks.
No time.
No break.
We start from 11 today and we finish at 5.
Stinky. Not even like 10 minutes, 20 minutes? No time to get food. You're all hungry, is that the point?
Because I have to move around buildings and up and down.
I know, okay. Alright, we'll make...
Very tiring and time
No, you don't have to tell me, I know. Okay, I'll tell you what, I'll make sure you have a break before your maths class starts, okay? We'll do 2 questions, I'll go through the answers, and don't worry, I won't let you starve, okay? He seems what?
Innocent.
Him? I know he's not innocent, though. I know it's an act. I know this. See, I can tell you're innocent. It sounds believable. Yeah, exactly. Little do I know, yeah. He's a criminal mastermind, is it? Okay, can I close these notes? Yeah?